Hey everybody, good to see you. I mean, good for you to see me because I can't see you. Um, Hopefully you just did the Wile E. Coyote worksheet. And hopefully we've had at least a conversation maybe a little bit about that. And you see the, how shall I call it? The symmetry of an object that's been launched vertically that reaches its maximum height and then comes back down. Hopefully you've seen the symmetry of that and how beautiful that symmetry is. That's what you were supposed to see. That this acceleration due to gravity on objects in and around the Earth, I shouldn't say in, I guess you can dig a hole, but the symmetry of those objects' motion is it's a thing of beauty. Rises until it stops, and then it falls. All at the same 10 meters per second squared of acceleration, the acceleration due to gravity, the gravitational field strength around the Earth. I mean, that's what we're talking about. So, I have here a little cart. Right there. This cart has a spring in it. It can shoot a projectile vertically, right? Much like Wile E. Coyote was shot out of the cannon, right? So let me show you that. Oh, meanwhile, hey, I forgot to mention, I'm obviously in the classroom, and you're not here because it's Wednesday, May 6th. I'm here, and you're not. I had to clean up my classroom and get it ready for summer so they could get in here and strip the floors and wax everything and all that stuff. So anyhow, this little car here, there is a ball in there, right? Spring loaded. And here's what's happened. If I hope this works. I'm looking like an idiot. So if I pull this pin out, that ball is going to get shot up, right? And that's going to come back down. Now, just like Wile E. Coyote, this is a cannon, shot out. Going up, stops, comes back down. We hope. That's the plan. As long as I don't move it around like this. All right. Here we go. Let's try it. Hold on. Yeah. Okay. Oh, I knew it was going to happen. All right. Let's try. Let's try a little less of a shot. How about this? I know. I need to put it. All right, here we go. Right there. How about that? That's pretty good. Got it? All right. So there's one. All right. Let's go a little higher. Here we go. Did it again. It's just not working for me. Oh my gosh. The table must not be level, or the cannon's not level on the car or something. I can't even get the thing. All right, let's try it again. Oh, it worked. It worked. One more. So it wasn't a fluke. That was a low one again. Why is this not? Oh, man. Ooh, okay, now this is the real test. It probably won't work, so don't worry about it. All right, here we go. I just got to hold it still. Oh boy, I got a bad feeling. Whoa! Okay, let's try that again. Last time. All right, here we go. Hold it still. Hold it still. Hold it still. All right, so that's what the car does, right? We get a Wile E. Coyote, and again, if we were to look at, say, fractions of a second, at each fraction of a second, just like we saw with Wile E. Coyote, on the way up and the way down, at the same height, it's going to be equal velocities, but in opposite directions. At each increment of time, whatever we look at. And of course, at the very top, it's not moving at all, it has to stop so it can change directions. What happens though if this car is moving like this and then I pull the pin? What's going to happen when it's launched up is the question. Hopefully you're pondering and thinking about that. What's going to happen? I mean, I guess there's probably three options. It's either, because it's rolling this way, either the ball is going to go up and shoot forward like this because the car's moving forward, or as it shoots it up, the ball's going to get left behind because the car's still rolling, and then the ball's just going to land behind the car. So it's either get launched out in front of the car, launched behind the car, or it's going to land right smack dab in the car like it just did a second ago when it wasn't moving. So think about that for a second. What do you think is going to happen? Pause the video if you need to ponder it for a while, and really, let yourself think about the possibilities and what you think might happen. And then I'll show you. Now, what's supposed to happen may not happen anyway, because you already saw this thing doesn't always hit the target if it's supposed to hit the target. And so if it's supposed to land ahead, maybe it won't always land ahead. And if it's supposed to land behind, maybe it won't always land behind. I don't know what's going to happen. I'm going to try my best. Let's go with just a little shot first. Just a little short up and down. All right. Here we go. I'm going to give it a little push, and I'm going to pull a pin. Y'all with me? Here we go. Of course you are. And unless you're not watching this, and then you didn't even know this happened. Ooh! It landed in the car. That was a little short jump, though. That was just a little short. Let's try that one again. Push and yeah. How about that? Uh-huh. Did you think it was supposed to land back in the car? I don't know. Let's see if we can get a little bit bigger. Jump. Here we go. Oh! Oh, we had a little problem. I lost the ball. Oh my gosh. Oh. All right. Try it again. It depends. I mean, sometimes this thing, it's got issues. Oh my gosh, come on. Ah, that was good. That was good. And let's go with a really high shot. See if I can get it. Oh, off the rim. I gotta do that again. All right. Now, what is this telling us? Like, oh, ouch. What is this telling us? Are you even thinking about that? What is this telling us about projectiles? I guess we'll conclude here in a second. Yes! That was killer right there. You all watch that again, like slow it down or something. Now, what is this telling us about projectile? Ow, my cabinet hurts. What is that telling us about projectile motion? I hope that you're seeing that what happens vertically and what's happening horizontally, they're independent. The one is not dependent on the other, okay? Because what happened to the ball bearing here, the projectile, when the car wasn't moving at all? It went up and down, landed in the same spot that it was when it was launched. What happened when it was rolling? It went up and landed in the same spot as when it was launched. Do you see the path that it traveled? It did this. Oh, look at that. Started here, got launched up, and then landed here somewhere. Oh, there we go. So, that's the shape of a projectile's path. It's actually a parabola. It's a parabolic path. Now, does the horizontal motion of this ball bearing since the car and the ball bearing are both moving horizontally, does that change the fact that gravity is pulling down on it once it gets launched upward? No. The horizontal and the vertical motion are happening simultaneously, but they don't affect each other. The vertical motion does not change what it's doing horizontally, and the horizontal motion does not change what it's doing vertically. So, when we're looking at projectiles, we have to handle both of those kinds of motion separately. What kind of motion did the car have as it traveled across the table? I would say constant velocity. I wasn't pushing it, I wasn't making it speed up. And I would say that, yeah, of course it's slowing down, but it's, I would say, maybe unappreciably. I mean, it wasn't being sped up or slowing down appreciably during the horizontal rolling here across the table. So the horizontal motion stays constant. Is the vertical motion staying constant? No, it's affected, of course, by the force of gravity, which means it's accelerating. So that's not constant velocity. That's like kinematics curves velocity. So these, it's those, all right? That's what we're dealing with here for the vertical motion. Vertical motion, those. Only now, instead of like delta x here, and delta x here, maybe it's delta y, because y is up and down. X would be horizontal, y would be up and down. And maybe instead of just VI and VF, maybe we should differentiate and say, hey, that's in the y dimension. So VYI and VYF. And instead of just A, it's a very specific kind of A right now. What kind of A are we dealing with? Well, it's not just A. It's actually the acceleration that's due to what? Gravity. That's little g right there. If you're dealing with a projectile and you're using kinematics equations, A is always going to be the gravitational acceleration. That's what we saw with the case of Wiley. That's little g. Delta t is still delta t. Delta x, I would say, is called delta y now, change in vertical position. And then your VF and your VI are vertical velocities like VYI, VYF. So you could change the notation a little bit to be more specific to projectiles and reminding yourself that we're only dealing with vertical when we're dealing with acceleration. And that means that the only other thing we have, oh man, this is, oh geez, I'm going to have a motion sickness or something. I wish I could be here to do all the videos. Like if I would just do whiteboard videos like this, I feel like it would be more interesting. So the only thing we have for the horizontal motion that was constant velocity, that's tumble buggy stuff, right? So we have delta x over delta t is average velocity, and that's not changing. That is the velocity constant of a projectile as it moves horizontally. Vertically, the kinematics equation stuff is happening. And that's why I suggested to change from delta x to delta y in your kinematics equations, because I don't want you to get confused that there is a delta x, the horizontal change in position of a projectile, but there's also the vertical change in position, and those can't both be called delta x. All right? So if you want, well, let's just do this. I'm going to write out what those equations would look like if you were to change the notation. So we would have delta y. I don't like that marker. Delta y equals, oh man, what is it? Vyi. Now you don't have to change that, I suppose. You can keep it just Vi and Vf. As long as you remember that it's vertical, then you'll be all right. Plus 1/2 little g delta t squared. So there's one. And the next one we have delta y equals which one is that one? All right, 1/2, and then the VYF plus VYI. Did I have that? Yeah, I had it that way. Times, oh boy, delta T. And then we had the VYF equals VYI plus G delta T, I believe. And then we had the VYF squared equals VYI squared plus 2G delta Y. Yep. So this stuff, though, that would be the that would be the re-notating here of changing A's to little g's and delta x's to delta y's, and then v's to VYI and VYF. Now, those velocities are different. Those velocities are different than this velocity. If you have a projectile that's moving horizontally, that's the velocity that it's moving horizontally. The vertical stuff, vertical, horizontal. You have two completely different sets of variables here. Now, the delta T is the same. Like when a projectile is airborne, it's going to be in the air horizontally the same length of time it's in the air vertically. All right? But its horizontal velocity isn't necessarily going to be the same as its vertical velocity, because the vertical velocity is changing the whole time. It's accelerating. The horizontal velocity is constant the whole time because it's not accelerating. And what else was there? The delta x, the change in position horizontally, where it lands horizontal away from where it was released, is different than where it is vertically from release point to landing point. So again, you're going to have two completely different changes in position, a vertical change in position and a horizontal change in position based on the situation. All right? So you have to make sure you're keeping the horizontal stuff and the vertical stuff separated. The only variable that is consistent in both, the delta T, is the same. That is the one common link. The link between the horizontal and the vertical is the delta T. So often in these projectile type problems, you will have to find the delta T from one, either the vertical or the horizontal, and use that delta T in the other to find whichever variable that you're looking for. Like for instance, if they ask you, hey, what's the horizontal range of the projectile? How far did the projectile go when launched? Then you may have to find the delta T somehow with this stuff and use that delta T down here to find out the delta X. Or vice versa. Maybe they're asking you something about its vertical motion or its vertical change in position or whatever. And you've got to find the delta T down here using the horizontal information that they gave you to use that delta T up here to find some other variable. So often delta T is the connecting point between the two. So I'm going to stop talking now, finally. Wow, look at that shine. Look at that shine. It looks pretty good. So I hope that you all are doing well. I miss having, our class time together and being able to hang out and chat and tell stories. And so sorry you've kind of had a raw deal on this whole situation. But I hope that this at least helped a little bit maybe. And then the whole Wiley thing, I'll have to post maybe a key about that, or I don't know what. But well, you will have already seen it because I won't post this until all that's done. So anyway, I hope you're doing well. Hope you're staying safe. We've only got a little bit more time left, and then you're done. And maybe I'll see you again somewhere down the line. Have yourselves a wonderful day. Stay safe out there.